Good morning, everyone. Welcome to the seventh and the final session of the workshop Nonlinear Structural Mechanics using Python. I hope you enjoyed the last 12 hours of the workshop. So, this is the last bit that is left, which is nonlinear analysis of two-dimensional frames. So until now we have seen linear analysis of frame structures. And we have also seen the nonlinear analysis of a single degree of freedom system. 1 minute, there is an issue. Open to my there seems to be a problem with my okay, now it's working. Okay, so sorry for the disturbance. So good morning, everyone, and welcome to the final session of this workshop on nonlinear mechanics using Python. So today we'll be looking at geometrically nonlinear analysis of planar frames. And the first, so this will be a combination. We'll be putting together the concepts that we saw in the last few sessions. So one idea is so we have seen the analysis. We already have the code for linear analysis of frames. And that has got a certain framework that you know. It has got assembly, enforcing boundary conditions, solution, and post-processing. And we have the code for the iterative solver. We have an iterative nonlinear solver for a 1DOF system. So in the last session, we looked at this problem of a 2-bar truss with a spring. And we solved this problem with the assumption of large displacements and rotations. The displacements and rotations could be large and the strings were small. So with this assumption, we solved this problem in the last session. The next idea is to put these two together. So this is a multi-degree of freedom, but linear. This is a single degree of freedom, but non-linear. So the immediate next step is to put these two things together. So before we can get to that point, so what is different in the single degree of freedom and the multi-degree of freedom system? So in the single degree of freedom system, you have one equation of equilibrium. You have equilibrium of forces, right? We have equilibrium of forces. If you remember, we looked at this joint and said the internal force is equal to external force. We had equilibrium of forces at one degree of freedom. So basically, we had a scalar equation. But in a multiple degree of freedom system, what we have is a vector equation. Say, for example, if we have something like this, an assembly of two bars, and you're subjecting it to a force P, then this is a multiple degrees of freedom system, and this has got 2 degrees of freedom, right? So this point can move downwards and it can also move rightwards. So this has got 2 degrees of freedom. Therefore, we'll get two equations of equilibrium, say something like this. F1, F2 external is equal to F1, F2 internal. So this is slightly more complicated to deal with, but there are ways to do it. So one approach is use the principle of virtual work. So what it says is that suppose we have a multiple degree of freedom system. Say you have a system of particles or some system of bodies, right? Let us take the simplest case of right. Suppose just take the system of 3 particles connected by springs, and you can have all kinds of forces acting on that. Say F1, F2, and F3. Now this set of forces and this will undergo some displacement. So if this setup is under equilibrium, then what it means is first globally the sum of all forces should be equal to 0. So this is the vector equation of equilibrium, and on every particle we have sum of F. Let's say every particle P, the sum of all forces on that particle P has to be equal to 0. So this is global equilibrium. This is the equilibrium of every particle. Now we can always consider an admissible virtual displacement field and call it delta U maybe. Right, so it means basically to this system, I'm displacing these particles by some amount. So the first one, I'm displacing it by some delta U1. I'm displacing this in the direction of force by some delta U2. And this I'm displacing as some delta U3. Now, what the principle of virtual work says is that, so this, if this system is in equilibrium, for a system that is in static equilibrium under the action of a system of forces, in the virtual work done by the external forces on an arbitrary admissible virtual displacement field should be equal to the virtual work done by the internal forces on the strain field associated with the same displacement field. So for example, in this case, if you take particle 1, it has got 2 forces acting on it, 3 forces acting on it. One is the external force F1, then it has got the spring force. Let us say this is spring 1, spring 2, and spring 3. So this has got a spring force Fs1 and Fs3. So for this particle, the the net external work done by the system of forces is what? It is just F1 dot del U1, assuming all are vectors, plus Fs1 dot del U1 plus Fs3 dot del U1. And this should be equal to 0. Why? Because this can be written as F1 plus Fs1 plus Fs2, entire thing dotted with del U1. This should be equal to 0. So this quantity is just the sum of all forces acting on this particle. So this has to be 0. This is identically 0. Next, so this kind of equation can be written for each of the above particles, right? So for this, similarly for this particle, we'll get something else. For this particle, you'll get something else. So if you see, there will be contributions from the external forces, and there will also be contributions from the internal forces. So if you collect these equations of equilibrium together, then what you get is that, so you'll get the net work done by the external forces, which is F dot del U1 plus F2 dot del U2 plus F3 dot del U3 will be equal to what? Will be equal to the these spring forces, right? So these are acting. So here there is an Fs1. Here there's an Fs1. So this Fs1 is acting on. This is acting on. If you collect the coefficients, right? So this Fs1 is acting on del. There's an Fs1 dot del U1, and there is a minus Fs1 dot del U2. So every so this will result in a term Fs1 dot del U2 minus del or let me put it as minus Fs1 dot del U2 minus del U1. And similarly, every spring force will have its own component. Now you can take all these to the other side so that you get this will be equal to Fs1 dot del U2 minus del U1 plus and so on. So just by rearrangement, you get a certain expression where the left hand side all has the work done by the external forces on the virtual displacement displacement at these points, and on the right hand side you have something like internal forces acting on some internal displacement, relative displacement. So this is for a system of particles, and for a continuum, for a for a continuous system, right? This particles are physics. So in mechanics, we mostly deal with continuous systems such as a beam or bar, beam, solid, and so on. So for a continuous body like this, it can be subjected to some forces. And suppose the body is under a body is in equilibrium under the action of some forces, static equilibrium. Then the principle of virtual work states that the net external work done, which is nothing but the integral of all. Okay, you can just think of it as the net external work done. Let me just put it as summation. So if there is a distributed force, you have to integrate it over the area over which it's acting. So, and we can also have some restraint here. So the net external work done, which is defined as summation fx dot del u fixed. And define the internal work as integral sigma del epsilon dV. So integrate over the entire volume. Sigma is the real stresses caused by F, and this epsilon is the virtual strains or the strain due to virtual displacements. So if a body is in equilibrium and the state of stress is sigma, and suppose the configuration is something u. So when you specify the displacement of every point on the body, the configuration of the body is known. So So if the body is in a configuration that is in static equilibrium, then the net external work done by the forces on an admissible virtual displacement field should be equal to the net internal virtual work done by the stresses on the associated virtual strains. So this statement should hold for all arbitrary admissible virtual displacement fields. Now this statement is equivalent to the equation of equilibrium, which so this means every point is in equilibrium, every point of the body is in equilibrium. Now coming to our case, suppose we are having let us say we are looking at our say we have a structure like this, we have a beam. Instead, let us say we have a frame element. That's the objective of today's session, right? So we have a plane frame element. And it has got all its degrees of freedom. So it has got F1x, F1y, M1, F2y, F2x, M2, and corresponding kinematic degrees of freedom are like this. So it has got U1, V1, theta 1, U2, V2, theta 2. So what will be the net external virtual work done by these? So you can consider the forces to be specified on the element and the displacements as the solution. So if you know the displacements of this element at the two nodes, then the configuration of the element is completely known. So that is one idea. And suppose take the forces to be constant and they do not depend on the displacements. So the forces are constant, do not depend on these displacements. And so this is the real displacement field. Let us call the real displacement field, what to call it, maybe capital D. And let us call the real force field F. So this is the correct solution. Now consider a virtual displacement field given by delta capital D. So delta capital D is the same thing, but everything with a delta. It's like a small disturbance to this displacement. So there's a delta U1, delta V1, delta theta 1, and you have a delta U2, delta V2, and delta theta 2. So think of the virtual displacements. So the body is already in equilibrium at some state. So it has got, so this element is in equilibrium under the action of these forces and this displacements. But now you're considering a virtual displacement field, which is like, think of it as perturbing this displacement by a small amount, delta U1, delta V1, delta theta. And in the process, you're keeping the forces unchanged. So you're making small perturbations to the displacements while keeping the forces unchanged. That's the idea. In that process, what will be the virtual work done by the forces on this? So the forces are remaining unchanged while you're making the displacements, while the configuration is from D plus delta D. Right, in that process, what will be the virtual work done? It will be summation. So it will think F2x, delta U2, and so on. Yes, you said something?
Yes, sir. It is F1x U1.
Yeah, that's fine. It's F1x delta U1. The virtual external work done is F1x delta U1 plus F1 by delta V1 and so on, right? That is fine. Now we can concisely write it as the, so suppose I call the degree of freedom, yeah, we can write it as delta D transpose F. So that is fine. Then what about the internal virtual work done? The internal virtual work done is that there's no shortcut. We have to do it fully. So it is nothing but sigma delta epsilon dV, right? So now first thing that we need to see is what is this delta epsilon. So let us look at when we have large deformation. So we need something called nonlinear strains. Nonlinear strains. So imagine there is a segment of the beam. So initially it is horizontal, and after deforming it goes to some other. So this segment has a length dx, and after deforming it has got some other length. So say this point is A, it goes to the point A dash, and the point B goes to the point B dash. So what is so suppose A has the coordinates x comma y, B has the coordinates x plus dx comma y. So suppose this point has the displacement u comma v. Then what is the position vector of A dash?
dx.
No, it's x plus u comma y plus v, right? So the point A has got the displacements u comma v, and B, A and B we have already given the coordinates. So after deforming, the point A goes to A dash. So the position vector of point A dash will be x plus u y plus v, because it has displaced by u and b. Now similarly, what is for B? It is B is already at x plus dx. Now it will move by, say, u plus some du and b plus dv, because this is a different point, right? So this is going this has displaced by u comma v. Unless it is rigid body motion, you will not have the same displacement here. Unless it is rigid translation, you will not have the same displacement here. So, but this is not rigid translation. These are deformable bodies. So this will have some other displacement u plus d, but it will be slightly different from the displacement at A, because these are nearby points. They are only separated by dx. So this is x plus dx plus du, y plus v plus dv. Now look at the length of S.
Why not x coordinate of b dash is x plus dx plus u plus du. B dash.
B dash is x plus dx plus u plus du, right? Yeah, plus there's a u plus du, right? Yeah, thanks for pointing it out. So this is yeah, this goes to u plus du, so it is x plus dx plus u plus du, right? Now look at the length of AB dash. What is the length of AB dash? It is square root of this minus this square plus this minus this square. So this minus this is just dx plus du the whole square plus dv square. Now, for first approximation, you can write du as du by dx and dv as dv by dx. So the length of a dash b dash will be square root of dx square into 1 plus, let me write du by dx as u dash square plus dv by dx is dx square into v dash square. So I can take this dx out, and what we have inside is 1 plus this square has to come here. Yeah, 1 plus u dash the whole square plus v dash square. So expand it, you'll get dx into square root of 1 plus 2u prime plus u dash square plus v dash square. Now we want a measure of strain. So strain is change in length by original length, right? So it is change in length by original length. So think of, so this is something like a dash b dash, length of a dash b dash minus the length of AB divided by length of AB. But what is length of AB?
Dx.
Dx. So this is just, so this is dx into square root of this thing minus dx divided by dx. So the strain is just So the strain is what? The strain is this thing, right? This whatever is inside. So it is square root of 1 plus 2u dash plus u dash square plus v dash square minus 1. This is the strain. Now, what we'll be looking at in this workshop is something called second order analysis. So there are various levels of nonlinear analysis that we can carry out. The usual linear elastic analysis that we study in structural analysis is a first order analysis. So there is no nonlinearity. We consider the deformed shape to be the same as undeformed, and yeah, there is no nonlinearity there. So that's a first order structural analysis. What we'll be doing now is a second order nonlinear structural analysis. In this, so we approximate the strain by its quadratic approximation, and terms of order higher than the quadratic degree are ignored. So here, if I use binomial theorem here, I can approximate the strain as 1 plus. So the power is half. So it is half into 2u dash. So this is supposed to be less than 1. Obviously, this will be less than 1. This is all slope and squares of slope. So they'll be very small. So it is 1 plus half into 2u dash plus u dash square plus v dash square. Um, yeah. And the other terms will be even higher order. So this minus 1. So this is nothing but u dash plus half into u dash square plus v dash square. So this is the strain we'll be dealing with. Now we are interested in the delta strain. So what is this delta strain? Delta strain is the virtual. This is what we want, right? So this is the virtual strain or the strain associated with the virtual displacement. So this virtual strain is something like, what is the change in, so if you recall, the force F is acting on you're perturbing the existing state of display. There is a current configuration. You're perturbing that configuration by some delta U, and this force is doing work on that change. Similarly, the sigma will do some work on the change in that strain. So change in that strain is something like you can. So this strain, if you see, this strain is a function of U dash and V dash, right? Now you're interested in changes in this strain. So if you can think of this change in strain as dou epsilon by uh, dou U dash del U dash plus dou epsilon by dou V dash del V dash. This is just a multivariable calculus, right? So you are interested in some differential change in the strain. So it is just this. So what is del epsilon? It is del U dash plus, that's a half, and then so this differentiated with respect to U dash is just 1 multiplied by del U dash, which is this. Here again do the same thing. So this differentiate with respect to U dash, you get 2 U dash del U dash plus 2 V dash del V dash. So the change in strain is actually del U dash plus U dash del U dash plus V dash del V dash. So look at the change in strain by making so this is where the nonlinearity comes from. You already have a body that is highly deformed. Now, if you make a small displacement, which is some del U, that is not going to create a small strain, which is some just del U dash, right? This is going to be associated with the existing state of strain as well, not just the increment that we are applying. So the body is in such a state, you make a small change to its configuration. The strains that are induced by the small change in configuration not only depends on the change itself, but also on the current state of the body U. So this is where the nonlinearity actually comes from. Now this is fine. So just plug this back into our expression for internal virtual work. So we have this del W internal is equal to integral sigma del epsilon, and del epsilon we just got it as del u prime plus u prime del u prime plus
v dash del v dash.
v dash del v dash, and integrate it over the volume. So let me split it into two integrals, one over the area and then over the length. Because we are dealing with prismatic members, you can say it is area is not depending on length. So x goes from 0 to L. Okay, so this is fine. Next, what do we do? So next, now, so this part is called linear strain, and this is the nonlinear strain. Okay. Now this is for, so if you recall what we considered here, this is just the stretching of one element, right? This is for one fiber. This is the stretching of one fiber. If we have bending, we also have the bending strain, right? So bending strain is what? Just there's no large deformation in bending. We are assuming bending strains are small. So what is it? Minus something.
V dash del v.
Minus y by rho. Right? If rho is the radius of curvature, it is just minus y by rho, which is minus y into d square v by dx square. So it is minus y v double dash, right? So v double dash is the curvature. Y is the coordinate along the length of the beam, the thickness of the beam. So this is the bending strain, right? So if you see moment is, stress is my by I, and strain is my by ei, and this m by ei is the curvature. So you get strain as some minus, there's a minus everywhere, minus y by rho. Assuming it sagging moments as positive and all the usual convention, right? Y is measured upward positive, sagging moments are positive, so compression comes on top side, so there is a minus sign. So the bending strain is this. So if you have bending, in addition to what we have here, which is contributed from stretching, you will have one more term. So the internal virtual work done will be integral x going from 0 to L over the area sigma. This will have del u prime plus, I will just add this minus y v double dash plus u dash del u dash plus v dash del v dash dA dx. Now this is also linear. So here also, okay, there is something wrong. This is epsilon b. But if you want, if you are imposing a virtual bending strain, that will have this del. And why is the del not applied to y? Okay, so this, let me do one thing. This is fine. So this means del epsilon b is equal to del. This is minus del b dash. So why am I not putting the del on y?
It is very less.
No, it is not very less. It is an independent coordinate. Right, x and y are the coordinates. This del is the change in the strain when you make a small change in the configuration. So you have some configuration, you're applying some virtual displacement and you're taking it to a slightly nearby configuration. So that del is the change in the strain that is brought about by the small displacement del u. You're making a slight perturbation to the displacements. Why will it change the y coordinate, right? Y coordinate is something you're fixing like this. XY is fixed. Similarly, for the beam also, you're fixing the XY coordinates like this. And you're making a slight change in the position of the beam. But the x and y coordinate axis will not depend on the virtual displacement field we are applying, right? So y will not have any del applied to it. So that's fine. So there's a delta here. Okay, so this is totally fine. Now look at these terms. These terms, the del operator is not multiplying any displacement field. So these are linear and these are non-linear. So they have a u prime del u prime, v prime del v prime. That's a product of the solution quantity. So this is non-linear, whereas this is linear. Okay. So this is what we'll be working with. Okay, so one more thing. So this is the expression for del W internal. We already have an expression for del W external. So what is our residual?
It is
So in
work
what
done,
case?
work done external minus work done internal.
Yes, very good. So now you get the point, right? So this is a scalar residual. That's the whole idea of doing all this. So in a 1 degree of freedom system, we only have one force component, and that force component is a scalar. So that here you can say del F external minus del F internal. But in multiple degrees of freedom, we are having many forces. So what you do, just dot product with the virtual displacement field and then get one scalar component, one scalar. So this will be the Newton, this will be our residual. This will be the work done external minus work done internal, where work done external is del D transpose F, and work done internal is that big expression we have, right? This expression. Okay, now we'll come to the, so this, just have this in mind. So this is integral sigma del u prime minus y del v double prime plus u prime del u prime plus v prime del v prime. This integrated over the volume. Okay, so this is what we need to, so this is the residual that we have to let it go to 0. Okay, so this part is fine. Now coming to a slightly unrelated concept of shape functions. So those of you who have taken finite elements will know what shape functions are. So if you take a bar, you are applying some arbitrary forces F1, F2, and it undergoes some displacement U1, U2. Now you see that the bar is under constant force. Bar is under constant force. So that's under constant stress also, and which means it's under constant strain. So how will the displacement field be? So for a constant strain, what is the displacement field? It will be linear, right? So the strain is the derivative of the displacement. Therefore, for a constant strain, the derivative of something is a constant, means that something has to be linear. So you just take u as some a0 plus a1x, which is in general a linear. So can we write it in some other form? As usual in our matrix form, it is 1x multiplying. Yes, very good. Okay, so this is a good thing. We have it. Next, now can we do something else? So what about, what is u of 0? We say u of 0 is u1 and u of L is 2. So the a0 and a1 can be obtained using these equations, which means, so what is u of 0? U of 0 means in place of x put 0. So 1 0 a0 a1 is equal to u1, and 1 L a0 a1 is equal to u2. Now plug these, like collect these two equations together. So you get 1 0 1 L a0 a1 is equal to u1 u2. Right. So this, we get one equation for the variables a0 and a1. So let us call this matrix M. What is a0 and a1? So a0 a1 is M inverse u1 u2. But what u of x? U of x itself is 1x a0 a1, right? So this means it is 1x M inverse u1 u2. So if you look at what M is 101L. So M inverse is 1 by L, L1 minus 1 0, right? So bring it back here. So you get it as 1x. Take the 1 by L outside. You get L0 minus 1 1 u1 u2. Now multiply these, right? Don't multiply with U1, multiply just with this. So we get it is it an L minus x by L. So we get an L minus x by L, and you get an x by L, multiplying U1, U2. So this you can write it as some 1 minus x by L, U1, U2. So what we have achieved is that we have obtained an expression for Ux as a linear combination of its values at the two ends. So given any point in the element, this writing pad is really loose today, I don't know why. So given any point x in the element, you can obtain the displacement of that point as a linear combination of the displacement of the two nodes U1 and U2. Displacements of the two nodes U1 and U2. So what is this? This is basically an interpolation. So you might be aware of the Newton Lagrange interpolation functions, right? You have something like summation f of xj Lj of x, right? This is an interpolation of f of x given xj's and f of xj's. So this is some kind of interpolation for where these are called interpolation functions. These are the function sampled values, and this is the interpolant. So similarly, here we are doing an interpolation. So starting from the nature of the strain, we said it has to be linear. Sorry, strain is constant. So the displacements have to be linear. And if it is linear, it has to be related to the end displacements. And the relation is actually this, right? So, and these are called the shape functions, interpolation functions or the shape functions. These are called shape functions. And let me call this just NU. Leave it. Let it be just whatever it is, right? So these are called shape functions. But just recall how we obtain the shape functions. So you might have come across the shape functions in a different format, but yeah. Okay. So what we did, we started off with some expression. We first started with 1x a0 a1. Then we said we substituted the end values and said it has to be equal. So we got a matrix M. We got a matrix M a0 a1 is equal to the degrees of freedom. Let me say D. Then I said a0 a1 has to be so this matrix, let me call P, right? Let me call it as a polynomial matrix P. And this M is something, right? M is just P of 1, P of 2. And this a0 a1, we said it is some M inverse of P. Therefore, the function U of X is polynomial times M inverse D. And this we call as the shape function matrix N. This is called the shape function matrix N. Now, can we do it for the beam problem, right? Can we do it for the beam problem? So what is constant in a beam? So this. So what is constant in a beam? We have a beam. It's subjected to some forces at the two ends. Let's call it M1, M2, F1, F2. So this is a beam. And is there any distributed loading on the beam? No. There's no distributed loading. Okay. So what is the shear force? So shear force, it is dV by dx is plus or minus q, depending on how you take the directions, which means the derivative of shear force is 0, which means shear force is constant. But what is the shear force? It is derivative of moment. So this is equal to some constant, say C0, which means moment is some C0 x plus C1. But what is moment? It is EI d square V by dx square. This is some C naught x plus C1. Now take this EI to the other side and make it some K naught and K1. So we get dV by dx is some K naught by 2 x square plus K1 x, and V is some plus K2. And V means you just integrate once more, you get K naught x cube by 6 plus K1 x square by 2 plus K2x plus K3. So it doesn't matter what K naught by 6 is, you just call it sum. So V in general for a beam element, the exact solution for a beam element without any distributed loading is cubic. So it is sum A naught plus A1x plus A2x square plus A3x cube. So this is a general solution for a beam element ended loaded only at its ends. Now what about so this is fine. This is totally fine. Now let's do the same procedure. So V of x is sum p times A naught to A3. What is P?
1 and x. 1x.
Only 1 and x. What is the size of this? This is 4 cross 1. Can it be just 1 and x? So just see, V of x is this. It has got 4 terms. It is A naught plus A1x plus A2x square plus A3x
It's
cube.
x square and x cube.
So it is 1x, x square and x cube. Okay. So what are the conditions that we have? V of 0 is V1. And then what are the end conditions for a beam element?
V of L.
Okay, is V2. Then that's all. How many degrees of freedom a beam has at every node?
4. Every node 2 degrees of freedom.
2 degrees of freedom. So we have only specified one. What about the other one? V dash of 0 should also be specified, right? It is theta 1 and V dash of
L is
theta 2.
Theta
Okay.
2.
Yes, yes. So let's arrange it in the usual format so that let V dash of 0 go up and V of L can come down. Right. So it's like first 2 degrees of freedom are together, next 2 degrees of freedom are together. So let's so what is it? So now tell me this V1, V2, sorry, not V1, V2, V1 theta 1, V2 theta 2. This is our degrees of freedom vector. This is equal to something. So this is so this polynomial matrix is actually P of x, right? So this is what? This is V of 0, V dash of 0, V of L, V dash of L. So the dependence on x is actually in the polynomial matrix, and everything else, this A is a constant that does not depend on x. So this I can write it as P of 0, then so
P dash of 0, P of 1
L,
L and
P dash of L. This is multiplying A0, A1 up to A2, A3. Okay, so this is a 4 cross 4 matrix now. This is a 4 cross 1 matrix. Okay, further. So what is this matrix? Let us call this matrix as M matrix. What is M matrix? M matrix is 1, 0, 0, 0. Then is it hard? P dash of 0, 0, 1, 0, 0. Then P of L is
1 L L square L cube.
L square L cube. Okay, then last one. P dash of L is
0, 0 L
0, 1,
0, 1, 2L 3L squared by
3L square. Very good. So this is the matrix M. So we can get this, let me call this as A matrix. So A matrix is what? It is M inverse degrees of freedom. But what is V of x? V of x is polynomial matrix times P of x times A. So this is nothing but polynomial matrix times M inverse D. Therefore, it is nothing but polynomial matrix times. So yeah, that's all. That's done. So these are the shape functions. So this is a 1 cross 4. This is 4 cross 4. This is 4 cross 1. So this is the shape function. So the beam element has got 4 shape functions. Now let us derive it in Python. We can also do it manually, but inverting this big thing is a mess. So let's do it in Python, right? So this is also I'll use this also to introduce you to the SymPy library. So you can use this symbolic. Yeah, so SymPy means you can use symbolic computation. So let me first define X and L as symbols. So okay, it may be too small. I'll zoom in. So I'll define X and L as symbols, sp dot symbols XL. Next, what do we do? So I need an M matrix, or let me have a P matrix. P matrix is, so to define a matrix, you say sp dot matrix, and then write whatever you want inside. So it is 1 x
square,
x square.
x double star 2, x double star 3.
Yes, very good, very good. Then what is the M matrix? M matrix is, we just got it. So I'll write it as sp dot matrix. So first row is 1 0 0
0
then
1
0 1 0 0
0 1 L comma L
L
square comma L double star 3 0
then
0 comma
no
1
0 1 L 2 L
3 L square 3 star double L double
3 L
square.
square. Okay, so this is done. So let's call the beam for shape functions as NB, right? And or just let's call it N. Shape functions are. So there's a slight difference here. So in SymPy, the matrix, if you write it as a row vector, when you make it a matrix, it becomes a column vector. So I'll just make transpose of this. Okay, so there's a slight difference between NumPy and SymPy. NumPy, this remains a row vector, but in SymPy, it makes it a column vector, even if you put it this way. So just make it a transpose. So now this is, and again here there's no dot notation. Here matrix multiplication is just star. So in SymPy, it is just star. So this P star M will be our shape functions. So I'll compute it, and then let me print N. So the good thing here is, okay, what junk is this? Okay, so what is wrong here? I got what is wrong here. Is it P star M or something else?
M inverse.
M inverse, right? Yeah, so it is M dot inverse. So that is the dot INV will return the inverse of a matrix. Okay. So run it. So these are the shape functions of a beam. Shape functions, you can think of shape functions as nothing but interpolant. Given the values of slope and displacement at the two ends of the beam, this is what we need to use to get the values anywhere in between, at any point x in the beam. So let me do one thing. Our aim is not beam. Our aim is a frame element. So what is our degrees of freedom vector? It is u1 v1 theta 1 u2 v2 theta 2. Now, but I have the shape function for v1 theta 1 v2 theta 2. So the beam shape functions, I'm writing them as 0, whatever this thing, 1 minus 3x squared by L square plus 2x cubed by L cube. And then x minus 2x squared by L plus x cubed by L square. X minus 2x squared by L plus x cubed by L square. Then corresponding to u2, so the beam shape functions cannot depend on u2. So for do that, I'll put a 0. And v2 is what? v2 is 3x squared by L square minus 2x cubed by L square. And last one is minus x squared by L plus x cubed by L square. So the objective of doing this is I want V of x is equal to NB of D. So D is 6 cross 1, where I'm also including the degrees of freedom U1 and U2. But V of x cannot depend on U1 and U2. V of x can depend only on the slopes and the displacements of the transverse displacements of the two ends. Actual displacement should not get into the interpolation for V of x. So I have to make the coefficient 0. So I'm corresponding to U1, I'm putting a 0, corresponding to U2, I'm putting a 0. So this is 1 cross 6. Fine. Similarly, what do I do for U of x? Let me say U of x I'll call n axial times d. Now, we already saw that U of x is 1 minus x by L, U1, U2. Now, can you tell me what n axial will be? So D is 6 cross 1, NA is 1 cross 6. So what will be n axial?
1 minus x by L, 0, 0, x by L, 0,
0. Okay, so this is perfect. So fine. Now let us define these two. So I'll say n axial. So first let me define NB. NB is, so let me just use this. It is n of, it's 0, n of 0, n of 1, 0, n of 2, n of 3. And then I'll say n axial is 1 minus x by L, 0, 0, x by L, 0, 0. Okay. So this is fine. So the reason I'm doing this is now I want to derive something called geometric stiffness matrix. So I want to derive geometric stiffness matrix. Okay, so this let us just have this here. Okay. Okay. Now, so why do I actually need it? I need it because I want to compute this integration. I want to do this integral. That's the reason I'm working with that. Okay. So so use those here, right? So what did we get now? So let me take this internal virtual work out. So let me call this internal virtual work done as this. Okay. Now, what is the interpolation we have? We have what is u? U is u, and this is u of x, right? U of x is NA times
D.
D. What is del u of x? It is also NA times del D. Okay, so this is it. So what it means is that we have a beam element and we are having some virtual admissible displacement field. So what is a virtual admissible displacement field? Well, for a beam element, the interpolation everywhere in between is that it is NA times D. So if the beam element itself has got, I don't have to redo it, right? So this, you can remember this diagram, right? So you have D, which is the actual existing configuration now, and delta D is a perturbation from this configuration. So this is the virtual admissible displacement field. So this virtual displacements also have degrees of freedom, which are virtual degrees of freedom, del U1, del V1, del theta 1. And the real displacements have U1, V1, theta 1. So here the interpolation also follows the same thing. These are the virtual displacements. There are no virtual shape functions because shape functions are just interpolation, right? No matter what the solution is, shape functions are fixed. So see, when we derived this, this just depends on x by L, and it just depends on x by L, nothing else, right? So this does not depend on load or the strain or stress or anything else. This is just dependent on the geometry of the beam. So shape functions do not depend on the deformation. Therefore, del u of x is just Na of x times del d. Okay, then what about V? V of x is n bending d, and del V of x is n bending del d. Now remember, sigma is, what is sigma a function of? Sigma is the current state of stress. It is held constant as you make the virtual displacement. So sigma is a function only of u and v. So if you change the current displacement, the current strain will change. As the current strain changes, the current stress will change. So this is a function only of u and v. So it does not depend on del. Okay, so that's good. Now let us write this. We'll expand this out. So I'll write this in two forms. So my first term is the linear strains plus the second term is the nonlinear strain, sigma u prime del u prime plus v prime del v prime dv. Okay. In the linear part, so this is the linear part. Let me call it del w internal linear, and this I'll call it del w internal nonlinear. Now let us look at the linear part. Okay, that's very easy. Del w internal linear is what? It is integral over the volume sigma
del u dash
u prime
minus y del v double prime
double dash
del
dv. Okay, so this dv I can do what I did earlier, 0 to L, integrate over the area sigma del u prime minus y sigma y del v double prime dv. Now sigma, we know it's a function only of the so sigma so sigma depends only on the strains. Say sigma is equal to E times epsilon linear. So what is epsilon linear? Epsilon linear is the one that is coming from bending minus, stretching minus bending, minus y times v double dash. So sigma is equal to E u dash minus y e v double dash. Substitute in this. So delta w internal linear is integrated over the volume. Sigma is, take the E outside, E is constant. So integrate this over the area and you have another. L. So you have E outside, you have 0 to L, integrate over the area. And this you can write this as u dash minus yv double dash del u dash minus u dash minus yv double dash y del v double dash, entire thing integrated over the area dx. This is dA dx. Look at the first term. The first term is u dash del u dash integrated over the area. So u and del u are functions only of x. X is not dependent on the area. Area is at every section. So you can integrate area and write it as AE. So first term is EA integral u dash del u dash dx as x grows from 0 to L. Okay. So what about the second term? You get y v prime v double prime del u dash. But what is integral y dA?
Volume, sir.
No. You are taking the moment of area about its centroid. It is 0. Yeah. So this is the definition of the centroid, and we are u dash is the stretching, right? It's the mid-axis stretching. Y is the distance measured from the centroid of the area. So integral y dA will be 0 if it is symmetric, right? Because if you say up above the neutral axis, above the centroidal axis, y will be positive, below it will be negative. So this product will not contribute. That's all. So from the first term, only one term we'll get. From the second, what will happen? From the second, you will get, similarly, this product will not contribute. it is odd power of y. The second product will contribute. You will get plus integral over the area y square del v double prime dA integrate over length 0 to L dx. Again, del v double prime does not depend on the area. Integral y square dA is the moment of inertia, and we have an E somewhere outside. We have an E sitting somewhere outside. So integrated, you get only two terms, which is EA integral 0 to L u dash del u dash dx plus EI integral del v double dash dx. This is del W internal. Okay, so this is del W internal linear. Okay, so we are almost done. So let us say now use the expression for del U and U dash, right? So U dash is n axial times d, and del U dash is n axial times del d. Similarly, V dash is n bending times d, and sorry, it's not dash. So if you have a dash, dash will appear on the shape functions, right? D is independent, so you'll get. So we want V double dash, so it is NB double dash D, and del V double dash is this thing, NB double dash del D. So substitute this into this expression, we get del W internal is equal to U dash del U dash. So it is say U
NA dash.
Yeah. So this you can write as so there's a slight thing here. The net result has to be a scalar, right? So U dash del U double dash, I can write it as del D. So this is like so what I mean to say is this is a scalar, this is another scalar, and the net result has to be a scalar, right? So what is the way to multiply this? So let me write this as del U dash transpose U dash, right? Just for the sake of it. Del U dash transpose is nothing but del U dash itself because it is a scalar, but that will ensure that the resultant. So this is like a vector transpose another vector of equal length will give a scalar. So that will ensure that the resultant is a scalar. Otherwise, if you put it in some other order, these are matrices and their multiplication will not make any sense. So here, let me write this as del U dash transpose U dash, which is del D transposed. So there's an AE by AE, del D transpose NA dash transpose U dash, which is NA D, and then it's integrated over the length. Similarly, second term, integral 0 to L EI. I'll write this as del V double dash.
In the first term, it is NA dash.
NA dash. Sorry.
NA dash.
Yeah, this is NA dash. Yeah. Thanks for correcting it. Yeah, it's NA dash. The second term, it is again similarly, it is del D transpose NB double dash transpose NB double dash D dx. Right? Now, does this depend on x? These two do not depend on x, right? Similarly, this and this do not depend on x. So I can take them out of the integral. So you get integral, I can write this as del D transpose integral 0 to L. AE doesn't matter, you can take it inside. So it is NA dash transpose NA dash, can take this AE inside dx, multiplying, this entire thing is multiplying D, plus you have a del D transpose, you have integral 0 to L NB double dash transpose NB double dash EI dx multiplied with D. So maybe you got the idea why I'm writing it as del D transpose, right? Because this will be equated to the virtual external work, external virtual work, where you have del D transpose F. So then you can take del D transpose commonly out and you can write F as something else. So that is what we want. So we want F internal, we want an expression for F internal. That's why we are doing all this, right? So this is fine. We got an expression for the internal linear virtual work done. So let us put these into that expression we have and see what we get, right? So this D is going to be there. Now let me just call this. So let me just call it del D transpose integral 0 to L AE NA transpose NA dash transpose NA dash plus EI NB double dash transpose NB double dash dx D. So why is it linear? This is linear because this entire term does not depend on D. Right? So see the form. So this is the the linear part of the internal virtual work done. So obviously the internal virtual work done should depend on the virtual displacements. Yes. So it is getting multiplied with the virtual displacements. But what is getting multiplied with the virtual displacements? Some force term. But that force term has linear dependence on D, and this matrix, whatever it is, it does not depend on D. So if you say this internal virtual work done, if you scale all the displacements of the current state by 2, the internal virtual work done on a given virtual displacement will be scaled by 2. So this one does not depend on D. And we'll quickly see what this term is, right? So go to this, what is this? Go to this one. NB and NA we have. So let me just call D and A as differentiation of NA. NA with respect to X, right? And let me call D and B as differentiation. So SP dot diff will do analytically differentiation of NB with respect to X 2 times. Right, so yeah, you can say it will so it says diff f of x x3 will return the third derivative of x. So this will return the second derivative of NB. So these are the things that we want. And we have 2 more symbols. Let me call SP dot, what are they? AE and EI. So let me say AE or EA, EI are SP dot symbols EA, EI. Okay, so now it's done. We'll yeah, this I have to convert to matrix. So this I'll do SP dot matrix of this thing. And I have an SP dot matrix of this thing. Okay, so this remember this will make it a column matrix. So I will have to transpose it. Okay. Now let us. So what do I call this? I can. Yeah, this one. So this does not depend on K D. Let me call this some. What happened? So let me call this expression that does not depend on D as some KE. So you'll quickly see why it is called KE. So KE is SP dot. So we want to integrate it.
EA star.
Yeah, so it is EA star, NB.
No, sir.
DNA, sorry,
DNA.
DNA, transpose
Star
star
DNA
DNA,
plus
comma. So this will be, yeah, we can do both together. Plus EI star,
DDNB star transpose star DDNB.
okay, limits x going from 0 to L. Okay, so this is fine. Let's evaluate this. Okay, there is a invalid limits given x 0 L.
L is not defined.
L is defined. L is there. So I think just make it x comma L. So it will evaluate it at L. That's also fine. Yeah, now it is fine. Now if you see what KE is, you will see something familiar. Okay. What chunk is this? This cannot depend on x, right? Oh, sorry. This has to be a tuple. This has to be x comma 0 comma L. Yeah. Now you see what KE is. So this appears familiar.
Yes, sir. Stiffness matrix of frame.
Yeah. Yeah. So this is the stiffness matrix of frame. This is the stiffness of matrix of the frame element in axis oriented coordinates, right? Where you have these zeros, so many zeros. When you transform it to some other coordinates, it will disappear. So this is the whole idea. We can also derive the stiffness matrix from the principle of virtual work. But you see, this is only the linear part. So when we do our usual stiffness matrix derivation, we assume that displacements are small, strains are small, material is linear, etc., 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 and finally we get to the same stiffness matrix. But that is only the elastic part. That's why it's called KE. So now let me write it. So del W internal linear is equal to del D transpose KE D. So have this as something. Then we have the other part, which is nonlinear, and that's the whole objective. So we can also do the same thing there.
Q transpose KQ. Like, it is similar to Q transpose KQ.
It is similar, but it's not the same, because that is a transformation. This is to return a scalar. So this is a displacement like quantity. This is like force like quantity. There both are dimensionless. There we had all angles, so this dimensionless, but here it is something different. Okay. So we had the nonlinear part somewhere. I'll just get that. Yeah, it is U dash. This is all fine. This is all shape functions. So this is the nonlinear part, right? So sigma U dash del U dash V dash del V dash. So this is fine. Now look at nonlinear part. It is integral 0 to L, integral over the area, sigma U dash del U dash plus V dash del V dash dA dx. So nothing here depends on area, right? So sigma is a constant. Here there is no y dependence. Sigma, you can treat it as a constant. So this can come out. So this can come out. So why is sigma a constant? If you see, sigma is just okay. I'll tell you why it is, right? So this right now have it as it is. So this again, if you take a second order approximation, if you consider the variation in sigma, it will be of higher order, right? So this sigma is so sigma is a constant in a given element, so it can be taken out. And this area you can integrate over the entire area, so you get a sigma A. So I'll just take this out. Sigma A. or rather, let me do one thing. So this I can write as, so this part is independent of
X.
yes, this is independent of X. So I can write this, no, not independent of X, this is independent of the area. U dash del U dash is not independent of X. It depends on X, but it does not depend on the area. U dash is the center line stretch. V dash is so U is the displacement along the center line, which does not depend on the area. And V is the transverse displacement of the center line of the beam. Even that does not depend on the area. So this is independent of the area. So you can take this out into this integral. So you get integral 0 to L U dash del U dash plus V dash del V dash. Then you have an integral over the area sigma dA dx. But what is integral over the area sigma dA? That is the force F. Force in the member, right? Sigma d. So you have, this is our frame element. You have at any section, at a section X, at a distance X, you have a section. In that section, you are integrating sigma dA. So what will that section have? That section will have some force F. But what is that force F? For equilibrium, it has to be equal to, it should be equal to what? It should be equal to, so draw the free body. So here you have F1 and here you have a force F. It's equal to minus F1 or F2, right? You have a plane frame element. You're cutting somewhere and integrating the force, integrating the stress. So that gives a force along the X direction. But this frame element has to be in equilibrium, no matter where it is. Okay, even consider the frame element in some orientation, but the X force has to be equal to minus F1 and which is equal to F2 because the element itself has to be in equilibrium. So wherever you cut that, you will have some force, and that force has to be equal to minus F1 or F2. And that is a constant, so it does not depend on X. Wherever you make the section, the net resultant has to be minus F1, which is equal to F2 for a given element. And what about this? So again, U dash is NA dash
D.
D. Del U dash is NA dash del D. And V dash is NB dash D. And del V dash is NB dash del D. Fine. So substitute this again, use that trick. So U dash del U dash, write it as del U dash transpose U so that you get a scalar so that the inside matrices make some sense. So you will be left with del W internal nonlinear will be what? The sigma dA will be the force, and that force does not depend on X. So that can come out. So you get an F outside. And then you get this. So you get an, so first thing, yeah, you get an F outside, then you get integral 0 to L. You get del D transpose NA dash transpose NA dash D plus del D transpose NB dash transpose NB dash D. This entire thing multiplied with dx. Again, del D dash D is common in both the terms. Take it out. So we get is del D dash, del D transpose F integral 0 to L NA dash transpose NA dash plus NB dash transpose NB dash integrated over X. This entire thing multiplying E. Okay, so this very good. We have got an expression for the internal virtual work, the nonlinear part of the internal virtual work. Now, where is the nonlinearity here? This one is it's an assumed arbitrary virtual displacement, so that doesn't matter. So where is the nonlinear? This is the displacement, the current configuration. Right, this is the current configuration. Now, where is the nonlinearity? Where is the nonlinearity? Yes. So this is This force actually is a part of the solution. The force depends on the current configuration. Very good. Yeah, you caught it quickly. So force depends on the current configuration. So this F is actually F of D. And the D itself is also appearing here. So it's some product form of D. It's not linear in D. But however, whatever is inside the integral is simple. Whatever is inside the integral is very simple. It's even simpler than the elastic part. Now let's, so therefore, so since this depends directly on the stresses or the force, this is called the uh, stress stiffening matrix or the geometric stiffening matrix. Stress stiffness matrix or the geometric stiffness matrix. So stress stiffness, because this part is there is no dependence of material. There's no dependence on the material properties here. Neither I nor E, nothing comes into play. And similarly, only yeah, those don't get into the picture here, and only F is affecting this matrix. So this is called the geometric stiffness matrix. Geometric stiffness matrix. So next, our task will be obviously to evaluate this matrix, right? So let's do that. So we got the KE. Now let me do KG. So we already have D and A. Let me also define DD. Sorry, D and B. We need it here. So D and B is SP dot difference is NB with respect to X. Okay. Now let me do this. So Kg is, so I need another variable which is force, or let the force be out. It's multiplying everything. So Kg is integrate. What should I integrate? N DNA transpose
star
DNA
DNA
plus DNB transpose
star
DNB over which interval? X going from 0 to L. So this is the correct syntax. So the variable, comma lower limit, comma upper limit inside this tuple, inside this parenthesis. So then I'll just print kg. Let's see what it is. DNB is not defined. Okay, I have to run everything again. Okay, so this 1 by L, 1 by 10, L by 10. Okay, fine. I think this is totally fine. I'll copy paste this. How to copy paste? I'll copy this and put it on my presentation. So this is the contribution from this thing. So this is this is kg. This is kg, but there's an F multiplying it. Let us just check it is correct against the textbook answer, because it is correct. I remember it's L 6 by 5, L by 10, and so on. Let's just check that once. Yeah, so this is the one. Do it in split screen mode. Yeah, so fx2 is our F, and there's an 1 by L outside, and here, yeah, so it is 1 6 by 5 L by 10 minus 6 by 5 L by 10. It is symmetric, then 2L square by 15 minus L by 10, and is L square by 31, 6 by 5 minus L by 10, 12 square by 15. Okay, fine. So it's all right. The stress stiffening matrix is correct. Okay, now what? What next? So what is it we have?
And
Yes.
we have to add the nonlinear integration and the linear part of integration.
Yes, yes, very good. So the internal virtual work done, nonlinear part of the internal virtual work done is del D transpose kg
KE
D.
D set.
Then del W internal, the linear part is del D transpose KE D. Next we have del W external, which is del D transpose applied force F. Sorry, let me say it. F external is what we are applying. Right. So this our residual is what? Our residual is external minus internal. So what it is? Our residual is. So let me use small r because it is a scalar. So it is. I can say del D transpose can be taken commonly out, and I have F external minus
KE plus KG.
KE plus KG. Here kg is a function of D. Remember, kg is a function of D times D. So this is equal to 0. This is the equation that we want to solve.
Kg is F times that matrix, no sir. So Kg is not a function of F also.
Kg is a function of F, but F is a function of D.
Okay, sir.
So you can say kg in general is a function of D. Yeah, you can put kg is a function of F. That's also fine. Kg is a function of F, but F will confuse. It shouldn't be F external. It is internal force F in an element. So it is kg a function of D. So finally, this is the residual that we want to force to 0 by Newton-Raphson. So and this holds for arbitrary D. This holds for arbitrary del D, which means what is our equilibrium equation? F external minus what? Ke plus kg, which is a function of D. This is our equilibrium equation. So why did we do all this? Why did we really do all this?
F external must be multiplied by delta D. Yeah, okay, no, sir.
Yeah, we don't need rates. Yeah, this one.
Okay,
So we did all this because we wanted to get an expression for the internal force. This, when we have nonlinearity, when we have large displacements and rotations, the internal force is not, it's not easy to get it. So we use the principle of virtual work, and we know what Ke is. We know what Kg is in terms of the force. Therefore, we know what the internal force is. So this is the expression for internal force. Now we are going to set these two. We are going to solve for this. Okay, so our whole point of doing all this is we wanted an expression for internal force, but we also have an extra benefit. So we got the elastic and geometric stiffness. So we also have an extra benefit. Now let us call this R of U as the vector, R of D as the vector residual. This is the vector residual. It is F external minus F internal. And F internal is this Ke plus Kg D. What is now? So let's set up a Newton-Raphson, right? So let me make a guess. Let's start with a guess dn. Let me start with a guess dn. And what should be the correction? So if I have a dn, that will have a residual R of dn. What should be the correction to get it to 0? What should be the correction in every iteration? So let me call the correction as delta D. So this delta is different from the virtual displacement, right? This is a true correction. So it is R of dn plus, by making the correction to the current guess, I want this to go to 0. So I expand it. So it is F external minus Ke plus Kg of dn plus delta d. Kg is a function of this, kg of dn plus delta d. Multiplying dn plus delta d. This has to go to 0. Right? This is what I want to ensure. Simplify this further, I'll get f external minus. So this will multiply. There'll be one part that multiplies. So kg itself, to a first approximation, you can take it as ke plus kg times dn minus ke plus kg times delta d is equal to 0. Right? We can write it this way. When delta d is fairly small, we can write it this way. But what is this? What is this?
It is R of D. R of D.
R of dn. Yes, it is R of dn. So this itself is R of dn minus ke plus kg delta d is equal to 0. Now this is the system I need to solve for. So what is the Newton-Raphson iteration? The Newton-Raphson iterations are as follows. So first start with a guess dn, then form R of dn as f external minus f internal, which is, yeah, you just make it f internal, right? You f external minus f internal. F internal is a function of dn. Then form something called the tangent stiffness matrix. So this is called the tangent stiffness matrix because it relates increments in d to increments in this one, right? This so it's like if you have, so this is the internal force. So this internal force, if you increase it by some delta d, this is the change in that, right? So this relates incremental changes in the displacement to the incremental changes in force. So it's the tangent to the force. It's the tangent to the force displacement curve. So form tangent stiffness matrix as ke plus kg. Then solve for delta d as ke plus kg delta d is equal to the residual. Right? Then update dn plus 1 is equal to dn plus delta d. Then do the iterations again and again till some error is minimized. So we'll now implement this for some simple problem in our code. Okay, yeah. So yeah, we're almost out of time, but let's do it. This is the last session. So any doubts here? I didn't ask. So I hope it's clear. I was a little fast today because we have a lot to finish. But if there's any doubt, you can ask me. You can post. Okay. Okay. So this is fine. This is the iteration we want to implement. Now let's go to the frame code that we have. Right. I've already posted it in today's this thing. So this is done. This is the geometric stiffness we want. I can say print kg. Right, this is the geometric stiffness. Let me just copy this so that I'll use it in my code. So this is just a copy of the linear frame element code. I'm editing it. Okay. So this plot I'm not going to touch. The frame stiffness I have renamed it as elastic stiffness because this is only the ke part, not the kg part. This also I'm not going to touch. Then I'll go to frame geometric stiffness. So in place of whatever I have, I'll just put this, whatever I copied from there. Okay. So in place of that, I have this. This is the first row, second row, third row, fourth row, fifth, and sixth. Why are these in? There's no F by L because it's already there. So this is the matrix that we want. It depends only on L and F, right? So the arguments that will get into kg are only L and F. Okay, then it will return kg. Assemble global stiffness, we are not going to touch. That's the same, right? There's totally no difference in the logic. All the transformations, all the element assembly, nothing will change. They are the same. Enforcing boundary conditions also, there is no change, right? Wherever you have something, yeah, there's no change here. It's just this is fine. I'm just thinking of something. Okay, fine. Let's see. Now, problem definition, there'll be some slight changes, right? So so which problem are we solving for? We didn't decide that. So let's do something that is easily, that can be checked easily. Okay, so let me, yeah, I would be happy to do some bigger problem, but maybe I'll give it as a assignment or something. So let's take this problem. Let's take this problem of buckling of a beam, buckling of a column. So buckling involves some nonlinearity. Okay, so this, let us say I'm interested in the buckling response of this as the load increases. Okay, so I suppose I'm interested in this buckling response. If you do a linearized buckling analysis, you will get some solution. You will have a governing equation as something like this: EI rho square m by sorry EI dou square y by dou x square, dou square b by dou x square plus py equal to 0. I think this is what you'll get. Yeah. So this is the governing equation if you solve it in uh, right. This is the linearized buckling analysis. And you'll get a solution of the form y is equal to a sine n pi x by L. And this a can never be determined. We don't even know what a is. A is just some arbitrary constant, but we'll get a critical load. We get a P critical load as pi square EI by L square. But when you do a nonlinear analysis, which we'll be doing right now, we do a nonlinear analysis, you can actually get the deflected shape. You can actually get the deflected shape. So to do that, let me first do one thing. So let me discretize the column with some number of elements. So let me discretize the column with say 2 elements. So I'm applying a force P here, and I'm keeping this, keeping the bottom fixed. But this itself will not buckle. If I just apply this, it will remain straight forever. In order to so in buckling problems or in any stability problem in nonlinear analysis, so the problem is in buckling, until a certain point, this will just respond linearly. Then beyond some point, you have a bifurcation. It can either go linearly or it goes to the other solution, which is the buckled solution. So that's the idea. Now we have a buckled solution, but to trigger the buckled solution, we need a small bias. Even in real life, if there is no imperfection, there's no all loads are concentric. A column can remain straight even above its critical load. So the critical load is the point where you have two solutions simultaneously existing. But in reality, there are some imperfections. There can be some slight disturbing loads, which will cause the column to slightly go away from its equilibrium. If the column is stable under the given configuration, if the given configuration of the column is stable, it means the column under slight perturbations, if you remove the perturbation, it will come back to its original point. If not, it will go farther away. So in reality, let's have a small perturbing load. Let us call the small perturbing load as alpha P, where alpha is some very small constant. Say alpha is some 10 power minus 4, which is very small, right? It's just enough to cause some perturbation, but it has no effect on the beam itself. Okay, so let us see. Let us see how this behaves, right? So, okay, what is the nodes matrix? Now so let's make it 1, 2, and 3. Let us make the length L. Make the length L. So nodes matrix is 0, 0, 0, L by 2, 0, L. This is the nodes matrix. What about LMs? LMs is simple. It is 1, 2.
1.
Yeah, sorry, 0, 1, 1, 2. Fine. What about the boundary condition matrix? Boundary conditions are at 0, true, true, false, and at 2 we have true, false, false. Right. So this is at 0. At 1 there is no boundary condition. You are applying a force. At 2 we are having true, false, and false. Okay. Okay. Anyway, there will be some changes to it, but let's first put this in. Okay. Let's put this in first. So A and EI, let's take some values. Okay. I'll take it from the book. So that we can check the answer correct directly. So this is L is 8 meters. A is 1.27 into 10 power 4. Okay. A is 1.87 into 10 power e power minus 4. This is an mm. I is 3.6 into 10 power 7. I is 3.6 into 10 power 7. And this is 10 power 4, not 10 power minus 4. Right, this is 10 power 4, 10 power 7. E is 2 into 10 to MPa. So you have to make it 2 by 10 power 6. So 2 into 10 power 5. Right, so it's 2 into 10 power 5, and the final answers will be in kilonewtons. Right, so yeah. So length is 8 meters. So it is 0, 0, 0 L by 2, and then 0 L. LM 0, 1, 0, 1, 2. Bound 0, true, true, false. True, true. True, true, false. And then at 2 we have true, false, false. Load, there's an issue. Load, let me. So let's see what is the load they're getting. So it's about 1137 kilonewtons. So it's let me load up to a value of. We cannot exceed it. So let's just put 1100 kilonewtons. And then 10 power 3 Newton mm. Okay, I think units are consistent. So this, yeah, units are consistent, no issues. So what are the forces? So F initially we'll fill it with zeros. It has got 9 degrees of freedom, and then at the 7th point we're applying minus P. So that's also correct. Then so here we are not directly going to assemble the stiffness matrix. So now we have to, yeah, you can tell me what we have to do, right? So yeah, you can tell me what you have to do. So I'll use this. So this is like one iteration of the Newton-Raphson, right? So we're assembling the stiffness matrix, and we are enforcing boundary conditions, and we are solving. So this is like just one step. but we have to do many times. So recall what we did in the last. So I'll say open nonlinear truss, right? What did we do last time? We had two loops. One loop is to increase the load, and another loop is to look at the displacement control is fine. We have look at the force control solution. We had one loop for increasing the load, and for every increment of the load, we had to ensure that the residual is going close to 0. So now we'll do the same thing. Okay, so now we'll do the same thing. So first, let us construct a loop outside. So first thing, this is the total force we are going to do the simulation up to. So f of 7 is the total force up to which we are doing the simulation. So let's say, so I have to split it up into many parts. So let us say for first let us define number of steps. Number of steps is equal to how many steps can we take? Let's take 100 steps, right? Then for II in range num steps, we need a force increment. So let's call the force increment as del F. The force increment is equal to what? F is the total force vector. What is this? This is not needed anymore. Okay, change the shape. Yeah, so what should I do? What I'm doing is first, I have a total force of 1100 newtons, 1100 kilonewtons. I'm applying it in steps of 11. So yeah, can you tell me the next steps? What should I do? First, I have to divide the load into small pieces, right? So del F, what is del F? Del F is F by num steps, right? Okay. Then I have divided the load into this thing. So this I can call it as F external, right? So now let me have an F external is zeros. So initially F external is zeros of size 9. So it is NP dot zeros of size 9. So initially I don't have any external force. Then I have to apply the external force in small steps. So in the first iteration, I'll do F external is equal to F external plus del F. Yeah, this should come after defining del F. I'm applying external force. Very good. Next, what should I do? I need an initial guess. Initial guess for what? What did we do last time? Last time we see, first thing we did is there we had an external force. We took an initial guess as the converged previous iteration value, right? So we started with forces all 0. Forces going in 1D. In 1D, there's no problem. This is an array. Here it will be an array of arrays. Then we said we initialized the load displacement degrees of freedom to 0. Let's do the same thing here, right? So let me call U. So before starting the iteration, I have initialized the external force. I'll also initialize degrees of freedom D. D is what? D is also NP dot zeros of yeah 9. Now I want my degrees of freedom. The current D should be the previous D. So I have an estimate. So my first guess will be zeros. Okay, so my first guess will be zeros. That's okay. Then what do I do? And what should I do?
D of I minus 1.
D of I minus 1. That's okay. So now we can make it more efficient because D of I minus 1, we don't need to store it. Right? If you see, we only need the final thing. But if you want, we can also do that. So okay, you're learning it only now. So let me make it zeros of so it should be an array of arrays. So let us make it a matrix of number of steps. So it's like size, it will have 100 rows and 9 columns. So every row will be one. Every row of D will be one solution, right? Very good. Then, so you said D of Di is equal to D of II minus 1, right? Is it that is what we did? Yeah, Di is the current estimate, that is equal to D of II minus 1, but only correction is it has to start from 1. Okay, good. Then what do? We need to find the residual, force residual. How to find that residual? How to find the residual? Use this. So if you see what we did throughout today's thing, as I said, all that hard work we did into doing all this calculus and finally getting at this equation is to get an expression for the internal force. This is the internal force. But how do we get the internal force? You have to do everything. You have to find the geometric stiffness matrix. You have to get the this thing, what it is, elastic stiffness matrix. Find the tangent. Assemble it. After assembling, you get one global stiffness. Multiply it with the current guess D. That is the internal force. Let's do that, right? So, so now I need to also have a stress. So for computing the geometric stiffness, I also need to have a stress vector. So let me call a vector called stress vector. Or let me call a vector called because force I'm using here, I want a stress vector. Let me call it stress vector. So why do I need a stress vector? Why do I need a stress vector? See what we are doing here. For getting the geometric stiffness matrix. Okay, what is wrong here? Something is not closed.
It is an extra one, sir. It can be deleted, that one.
Yeah.
We have to update force.
Yeah, we need the force in every element, right? We need the force in every element. So, so we need a stress. We need the stress. Let's call it stress because force is like force will confuse with the global force. I'll also call it stress here, or I'll call it to make it more. I'll make it stress here. No, but everything I have to change. Let it be F, but while calling it, I'll call it stress. So initially, I also need a stress vector. So I'll initialize the stress vector to zeros. So while I'm initializing, so this is like splitting the load. Then here I'll call this step initializing displacements, forces, and stresses. Okay, so this first thing is I'm making the forces 0, then I'm making the displacement 0, then I have to make the stress in every element 0. So how do I initialize it? Stress is equal to what it is?
NP dot 0.
Yeah, NP dot zeros. But how many zeros?
9.
Why 9? Where is the force coming in? It is an element force, right? So for one element, how many forces we have? That's why I said don't confuse. It's not force. It is the stress. It is the axial force inside an element that has got only one value. It is constant in one element, right?
Okay, sir.
So this will be how many zeros? 2. Yes. So it will be number of elements, length of elements. Very good. Okay. So stress is initially 0. Okay. Now what do we do? Now we have to get into the Newton-Raphson iterations. So let's compute the residual. R is equal to F external minus. Okay. We need the K. So let me do this. Assemble global stiffness is there, right? So this this is required. So let's say assemble global stiffness. This is fine. We also have to enforce boundary conditions. That's also fine. So while assembling the global stiffness, there is a slight change, right? So there is assemble global stiffness. There is no function frame stiffness now. Okay, so while assembling global stiffness, this should also take into account the stress. So that change I will make here, right? So this requires the material properties A, I, E, and also it requires the stress. So I'll say it also requires stress. So this assemble global stiffness function will also take stress as input. Now coming to this point, so K will have two components. So let me comment out. Sorry, what happened? So K will have two components. So this can be commented out. I'll say K global, K elastic is frame elastic stiffness of A, I, L, E. It should not depend on anything else. It can depend only on A, I, L, and it should also depend on alpha. A, I, L, alpha, and E. Sorry, A, I, L, alpha, and E. Right? Similarly, K geometric. K geometric is frame geometric stiffness of what it depends on L and F. Okay, so now there is a so this we should also do the transformation here. So whatever we did for elastic stiffness, do it for the geometric stiffness also. So this is there. Just copy paste it here. In place of KE, just put KG. So do the same thing. It will take alpha also as an input. So this we derived in the axis aligned coordinates. We have to transform it back. So this get in alpha and kg is equal to so this I can call k dash kg dash. This is kg dash. This is kg dash. And this is kg. Fine. So this will return the transformed elastic stiffness matrix and the geometric stiffness matrix. Next, what do we do? We'll say something called KT is the tangent stiffness matrix. It is KE plus
KG.
KG. Okay. Or let us call this small k because we don't need to edit the rest of the code, right? This is the tangent stiffness matrix KE plus KG. This is fine. So here there's no change. Assembly is exactly the same. So yeah. So now assembly will be done. After assembling, it will return the tangent stiffness matrix here. Okay, so this is the assemble the global tangent stiffness matrix. Okay. Now, so one thing is missing here. Just wait. This F. What is the F here? We didn't define it yet, right? So into the assembly code, the entire stress vector goes, which is the stress in all the elements. But we want the stress only in the current element. So in this, you need to do an extra correction. So F, just like how L and alpha are, we are finding, similarly F is current stress of II. Right? II is looping over all the elements. So corresponding to every element, there'll be a stress, and only the stress of the current element has to get into this one. Okay, so this is fine. This is also fine. Now assemble the global the tangent stiffness matrix. So you will get something which is KT. Then what is the residue? Then enforce the boundary condition. That's also important. So enforce the boundary conditions. Then what do we do? Then form the residual. Form the residual. R is equal to F external minus K dot di. K dot di. Good. So I think it's okay. Yeah, this is okay. Now what should we do? We should check if R is less than something, but R is a vector here. So let us take the norm of R, right? Let us say res is equal to NP dot linear algebra dot norm of R. We'll take the second norm of R and then see if it is less than. So now what is the y? We can copy paste. The rest we can copy paste from this code. So this you see, you need a counter, you need this, update L and stuff. So let's do this. So start with some counter while R is greater than something. So R naught is also this. This is also R naught. R0 is this. And this I'll make it. This is also res 0. So this will be, well, residual is greater than 10 power minus 4 res 0. Then make kk is equal to kk plus 1. We are increasing one iteration. Then okay, you can refer to the slides, right? We wrote down the steps here. In Newton-Raphson, what should I do? I have a guess, form the residual, find the update, right? Yes, yes. So first, we have the tangent stiffness matrix. Where is it? We have this tangent stiffness matrix K. We have this is the K obtained from di, and this is the residual obtained from dn. So what is delta d is equal to K inverse R, right? So just have this code as reference so that these are all fine. This is fine. L and all will be automatically taken care. I'll say how. So we are forming the residual. And then we have the Jacobian. Jacobian in this case is the tangent stiffness matrix. Then we are finding the update. So let's do that. So update this. We already formed the Jacobian. We already formed the residual. Yeah. Now delta D is nothing but K dot NP dot lineage dot solve. Yeah, it's already here. Instead of K comma F, it is K comma R. Right? Okay. So form this residual. Okay, this is fine. Solve this, then update. Right? You have to update it. What should we update? We should update D. So di is equal to di plus delta D. Right? So this was our initial. So update the delta D and then recompute the residuals. Then do this again. So now residual is equal to fx minus this thing. No, you have to do everything again. So this part has to be done again. Assemble the global stiffness. So basically this part is compute internal force. So assemble the global stiffness, enforce boundary conditions, right? Then what? assemble the global stiffness, enforce the boundary conditions. Then you have to check the residual, right? You have to check the residual. So see what we are doing. First, we are solving this. We are getting an updated displacement vector, but at this stage, you should also update the nodal coordinates. So now let us have a subroutine called update. Update, right? Let's call this update. Just worried about this. Yeah. So let's call this function called update stress or update solution. Let's say update solution. What all it should take? It should take di, the current nodes, and then so just think of it. What happens, right? When di is getting updated, it means there is a displacement correction. So so the displacements at every so the nodal positions are changing because you're having a displacement correction. The nodal position will change, and correspondingly the stresses will also change because it's in a different configuration. So stresses will change, displacements will change, and the nodal positions will change. So let us say you need to give in the nodes, you need to give in the stress, and you should also give in the LMs. Now let us write this update function so that will finally complete our code. I can also put it here. So this is stress update, stress and displacement update. So here I'll have a function called update. What it is, update with these. Okay, so first let us update the displacements. Update nodal positions. So we also need, so di is a degree of freedom vector, right? So di is the degree of freedom vector. So first thing I need to do is, so nodes has two things. So for every node, for ii in range of length of nodes, I loop over all the nodes. I'll say x coordinate is what? X coordinate of ith node is nodes of ia comma 0, right? And y coordinate is nodes of ia 1. Yes. Now what is x becoming? If we have a displacement vector, first node, what is the first x displacement? It has 3 degrees of freedom per node. So 3i plus 1, 3i plus 2. These correspond to ith node. So for first node, it will be 0, 1, and 2. For the second node, it will be 3, 4, and 5. So the x displacement corresponds to 3i. So it plus di of what? It is 3 star ii. And here it will be plus di of 3 star ii plus 1. Yes, good. Okay, good. So this is fine. This gives us the updated nodal positions so that as the geometry is changing, we'll also track the changes in nodal positions. That's good. Then what do we do? Then we have to nodes plus vi di. Okay, stress update. Yes, stress update. So here we have to loop over elements for ii in range len LMs. Okay, so for every element, so stress of so first we have to find the stress. How to find the stress? How do you find the stress? So for every element, first again you have to develop the for every element we have the element displacement vector, right? We have the elements displacement vector. We have the element stress vector. Okay, I can actually write it down. So first find the element displacement or element local displacements, right? Local displacements. So for ith element, what are the degrees of freedom? So let me call the displacement vector u. U is equal to, or just like as we did earlier. Like, so what is node 1? Node 1 is LMs of ia comma 0. Node 2 is LMs of ia 1. Then what are the element displacements? So u is so again we are doing the local to global mapping, right? So you will have 3 components. So first component 6 components. So first one will be 3 star node 1. So it will be di of 3 star node 1. Then di of 3 star node 1 plus 1. So this is the u of first coordinate, first node, v of first node, then theta of first node. Di of 3 star node 1 plus 2. Right? Then you have for the second node, di of 3 star node 2. Then you have di of 3 star node 2 plus 1 and di of 3 star node 2 plus 2. So this is the elemental displacements, but this is in the global, this is not axis aligned. This has to be shifted to the axis aligned coordinates. Or there's also another option. You can do something else. But anyway, leave it. Let's not do that. This is not an axis aligned coordinates. So what do we do? Transform. So copy paste this. Use this transformation matrix. Right. So this is not in axis aligned. This is in the global system. Use the transformation matrix. This has to come inside. So in the local coordinates, what is u? So in the local coordinates, okay, so we also need alpha then. So we have to do this again. Wherever that assembly operation is. Yeah, so we have to do this. Actually, we can copy paste this entire part. We need KE, we need KG. We need KE plus KG. We need up to this point. So let's copy this. Piece of the current element. This is fine. Yeah, let's just copy paste this. So we have got u, we have the solution. And here, let us do this. This is already inside. So let's do this. So get the coordinates of the nodes. We have already made the update. We have made the coordinate update. At L alpha F, right? Then we don't need F actually. We are going to find F. Then find KE. KE is the elastic stiffness matrix associated with that element. So find the elastic stiffness matrix, multiply it with the U. So what it will give the element force. So it will give element force as Ke dot U. Next, we have to transform this element force to um, local coordinates. So now use the transformation, right? Use the transformation. Use the transformation. Use the transformation. Right now, so use this to transform the element force. So you can call element force transform. LMF is equal to Q dot LM force. So this will give you the axis aligned forces. Now in this LMF, what is our stress? So stress of II is equal to stress of II plus whatever is coming from this one. So you got the element forces. From this, I'll call a quantity F as the axial force is equal to, we saw it's either minus F1 or F2. So I'll take minus of LM F of 0. So stress will become stress plus F. That's all. So this is the end of it, right? So this or just have the overall flow in mind. Later you can look at the code. I'm doing it fast because we are out of time. So first update the nodal positions. That is straightforward. So take X and Y, update it. Next you have to update it in the nodes. So you say nodes of actually you can do it right away. II0 is right. The nodal position is changing by this di. Then the stress is getting updated. How? First uh, find the global nodes corresponding to the local node numbers 1 and 2. Then in those global nodes, find the displacement. This will form the element displacement matrix in the global coordinate system. So element displacements in the global coordinates. Then you find the properties of the current element and transform it to the get the element stiffness matrix for this, get the element force vector, then you transform it to the local axis aligned coordinates. After you transform it to the axis aligned coordinates, you can find out the force, axial force in that element, and update the stress by that force. So one thing that I'm looking here is kg. Yeah, it should also have the components from kg. So kg is frame geometric stiffness, F, L, and this one. This one, what it is? The existing stress state, stress of II. So find with the existing stress, find the new, find the stress update, transform it to the local coordinates, and then update the stress. So what this should return? This should return a tuple of nodes and stress. So it will return the updated stress vector and the nodes. What happened? Return can be used only once within a function. Okay, where is it used again? Is there a return anywhere? This is the function. Hmm.
There's a gap between parenthesis and return. That's why you said.
Yeah, but that is not, that doesn't seem to be an issue. Update is fine. This is where the function is starting. Update stress update. This is a colon. Then here A is fine. Strange, right? It's let me call it stress update. Let's do anything. I'll run this. Let's see what happens. I put this is inside the loop, right? So this level is inside the loop, so it has to go back once. Yeah, indentation error again. I put it fully back, so that was the error. That was the error. Okay, so I think so this part will be stress update, and it takes in AEI. A. I hope it's right. AEIDI and my elastic stiffness is fine. Geometric stiffness is fine.
AEI is
Yeah, AI. Yeah, cross section, material, and then the updates. That's fine. Okay, so this stress update has to return what? It has to return nodes and stress. Okay, so once we get the stress, again assemble the global stiffness. This stress will get in. Find this thing, enforce, then find the residual. So R equal to Fx minus K dot Di. So this Di is the updated Di. It's the current updated Di. Now find the residual with that. Then find the norm of it. Res is equal to this thing. No change. That's all. So then when it comes here, it will check the condition. If it is satisfied, it will come out. Otherwise, it will not. Then lastly, I'll put this condition also. If there are too many iterations, let it print it. Okay. Let it print that. And let it print. If there are too many iterations, it will break here. And if it has converged, then it has to do the update. So V of II is equal to Vi. Similarly here, D of what did we call it? D is equal to like by 100. I made it num steps, right? So it is num steps. So here it is D of II is this. Let's hope there's no other IA. Yeah, IA is the time step. So here at this level, we'll have D of IA comma colon is equal to DI. Right, so DI keeps on getting updated, DI plus delta D, and so on. So yeah, so in stress update, it's not DI that gets in, that's actually delta D. dA is the full thing, so it's actually delta D. Delta D is what we got as the increment, so it is just delta D. That's fine. Okay, let us see. I hope it's all right. Now this is not required. Not required. So let us see if it runs properly or if there's any error. We'll see that. Okay. Tuple does not.
Name of the function set. When we define the stress update, where we define stress updates definition.
Okay. That's
Here
fine.
it
Right?
is delta.
Same name.
No, sir. D underscore I.
That's not a problem.
Be delta. Okay, sir.
That's not a problem. That is just a placeholder. You can use anything here. You can also put some B or C here, and that will work. That's just a placeholder. That's not a problem. No, the actual problem is we cannot assign to this. Okay, then I'll do this. This will work. Okay, so I have to do only. I have to do it the hard way. Let us call it update is equal to this, and nodes is equal to yeah. Let us try this. Oh, this is the problem. Okay. So this is a small change here. This can be. So this I have to make it. This I have to make it a list. Okay, let's run. Local variable f assigned before. Okay, reference before assignment. That's okay. That can be corrected. So this part, right? It's lm force equal to ke dot u. So here it will be. Okay, what was it? FL and alpha, right? It was actually alpha. I put the stress of I in the wrong position. STRS off. Okay, now it should be fine. Let's run. Okay, it ran without any errors. Oh no. Oh, divide by 0 encountered. Okay. L is 0 for some. Let us print at which. The 99th step this is happening, and KK 1. Okay. So until this point, let us see what it has done. So 99. Let's plot port let's see, d of, so this is the, so we are looking at the seventh degree of freedom, colon comma 7. Let us see what it looks like. So 10 power minus 8, 10 power minus 7 goes up to 10 power minus 6. And it is linearly increasing. Fine. So let us plot this. So import matplotlib.plt as then plt.plot. So let me plot the force versus displacement. So d of colon comma 7 comma f of, actually a comma lin space np dot f comma 0 comma 1100 comma, what is it? So I'll do a minus so that we get along the positive direction. Minus d p, and how many steps? Num steps. Let's hope it makes sense. Okay, it looks like it's linear, but okay, it's getting too late. I'll let us end it here. I'll share the debugged code. Right, I didn't have enough time to do it live. I'll debug the code properly and then I'll share it. So maybe for your practice, I'll put some problems. So you can look at the various functions in the code, change them, try see what happens, and I'll give you inputs also. You can try them because we have to conclude it. It's already too late. So, but the code is complete. Basically, the code is complete. It's probably something missing somewhere. So this, yeah. So let's finish it off. Okay. Yeah.
Thank you, sir.
Yeah.
Thank you so much, sir.
Yeah. Thanks for attending. I also had a good time. Most of you were very regular in the till the last session. I'm happy about it. So I hope it was a useful session for you. I hope it was useful. I hope you had something to learn from. And the codes, you can have them. You can use it. And I'll also, if possible, I'll send some problem sheet which you can work upon with some kind of mini project, right? You just take some truss member or a frame with an, after I debug this, right? I debug and upload it. And I'll also upload some problem sheet so that in you can also add it to your resume or something in case it helps. That you have written a code for some analysis, some simple analysis of some simple nonlinear analysis of some structure. So that will be helpful. That will be helpful. That will also help your coding skills. Right? That will help with your placements and stuff. And apart from that, maybe if you have any other feedback, you can tell me. I'll incorporate it in the next sessions whenever I take. There might be an extension of this, so I can extend it to so this is just geometric nonlinearity, right? So I can extend it to hyperelastic materials and plastic materials in somewhere else, right? There's an ISSS portal. I'm not sure if you're aware of it. ISSS portal by IC, and it's free. You can just log in. There'll be courses. A lot of courses are there. In case I upload one on that, I'll let you know, right? I'll post in this classroom group. Yeah. Yeah, I hope it was useful and I enjoyed it. I liked it. Lot of there was some interaction. Most of you are silent, but I was also happy with your answers you submitted for that small assignment. So keep working. It's an interesting area. Structural mechanics is very interesting for me. If you like it, yeah, keep working on it. Keep coding. It will help you with all aspects, problem solving and other stuff. And later, if you have any other problems or doubts with this part of the workshop, any doubts with the code, also you can post on the group. I will respond when I read it. Yeah. Anything else? Any other feedback you have? Anything you can tell me?
Yes, sir. In college, we learned only up to dresses. Here, we learned frames. It was interesting, sir. And here, how we got that matrix, frame stiffness matrix by integration, that was like magic.
Oh, okay. Yeah. That's in when you do finite elements, that is how people do it. When you write down the principle of virtual work, it's very simple. Rather than writing down all the equilibrium equations, that's very simple. When you do anything with energy, even in structural analysis, that's why throughout this workshop, whenever I wanted to compute any deflection, I started with the Castigliano's theorem. Because whenever you use energy, things become very simple. So yeah, that's anyway. I'm happy that you liked it. Uh, yes. Anything? Yeah. So feel free to write to me. My email is there, areshc@isc.ac.in. You also have access to that classroom. I'll keep it live. Whenever you have anything to post, any doubts or something, you can post on it. I know your exams are coming up, but I'll still post my that assignment with some 5 or 6 questions. There's no deadline. You can do it at your leisure time. Uh, enjoy coding and do it at your leisurely. Then you can also explore things, right? You can also add additional questions if you want. And
So,
yeah,
is this coding is what in the back end of the software, sir?
yeah. This is exactly the coding that goes behind software like STAD and Abacus. Yeah,
Okay, sir.
but they
Thank
have
you, sir.
little more because this is all toy problems, right? What we are solving is all toy problems. They'll have very optimized codes. So what we run,
In
they'll run it 10 times
time
faster.
complexity and space
Yeah,
complexity in order to reduce
yeah.
those.
Yeah, they'll take care of all those things. They'll have very optimized codes. Ours is just a conceptual thing. So these are not very optimal. Theirs will be optimized codes.
Okay, sir.
Yeah.
Thank
But
you,
it
sir.
will be yeah. It's the same code that I can assure. It's if there is a nonlinear geometric analysis in any software, it has to make use of all this Newton-Raphson assembly and everything else. Yeah. They may have additional codes for dynamics, etc. But yeah. Okay, it was very good to interact with you all. So, mm, yeah, have a good time. All the best for your all your all your future, right? Yeah,
Thank you, sir.
yeah, yeah. Thanks. I'll stop recording here and yeah, thanks.